Welcome back, ladies and gentlemen. Last time we finished up learning about position and displacement. Today, well, now, velocity. Velocity is the counterpart, the vector counterpart to speed. So they're going to have a lot of things in common, including their symbol, as we've already seen. But because they're similar, it often causes some confusion because people see things that look so similar, right? The V is the same, the equations are going to be very similar, and they're like, well, surely the numbers have to be the same, right? And it's like, well, sort of. I mean, you know, a goalie and a frontline hockey player both play the same sport, but they do very different things. The same is going to be true for this kind of stuff in physics. Speed and velocity are going to do different things. So, first things first, we're going to fill in our information. Velocity, and let's see what it says velocity is. Velocity is the rate of change in position. So before we had the rate of change of distance, now we're doing position. It is, of course, a vector. So we can give that one a good old circle. The units are going to be in meters per second or kilometers per hour. It can be pronounced kilometer or kilometer, just a reminder. Symbol. Symbol is going to be a V with an arrow. Arrow's critical. Now we're going to immediately move into the equation, and whoa, things are going to look really complicated now, right? Because I'm going to go V with an arrow, velocity, it's got an arrow, equals triangle D with an arrow, triangle T. Whoa, we've got a lot more symbols now. Now, on the plus side, these are all symbols we've already seen, symbols we already know. The triangle is delta, and we know that means change in. This whole thing can be rewritten. We can expand it. Do we have to? No, technically not. But if you don't know exactly how it works, if you're still feeling a little shaky on the math, then yeah, let's expand it. There's nothing wrong with that. So, what do we have here? Well, delta D is going to be equal to dF minus di. And delta T is going to be TF minus Ti. And they're both divided, just like that. So there it is. Oh wait, almost. I gotta put the arrows on. Now that's in your notes. It does tell you that. And this and this mean the same thing. There's no difference in them. Let's see what else it says. Velocity is a vector quantity. All right, I'll stick it down here. Velocity is a vector quantity. Velocity measures the change in position. Think of velocity as speed plus direction. Speed plus direction, because of course it's a vector. Vector has a direction. Velocity is calculated, broadly speaking, as displacement divided by time. Now, there are three ways to look at velocity, and they're going to look pretty familiar, assuming you've watched the video on speed. The first one on the list is uniform velocity. Uniform. What does uniform mean? We already talked about this once before, but a reminder, uniform means that everything is the same. There's no real difference, right? Everyone wearing the same uniform. That means that they are going to have the same overall appearance. So nothing is changing around the uniform velocity. So you're just moving along down the sidewalk, keeping the same. The next one on our list was average. Average, of course, is the total divided by the total. So this is what you're doing overall. And then the last one is that instantaneous. Instantaneous, much like we saw with time, just means that, you know, it's what's happening at this exact moment. So there you go. Uniform velocity, average velocity, instantaneous velocity. All of that, hopefully, it's pretty familiar. Now, we have an example directly underneath. I will do that, of course, on the board, show you guys how to work through it. And then we're going to work on a little bit more complicated example. And that one I'd like you guys to try with me, you know, with pausing the video and all that, but we'll get to that in a second. So, first let's take a look at the simple example. Shout out to the various students, by the way. A lot of people have been contacting me, especially in the last couple days, trying to get themselves organized and ready to go. It's good. Don't worry, guys, if you're feeling a little bit behind. Like, I know right now I'm making these things here on the 22nd. If you're watching these some other time, that's fine. Just so long as you get through it all. Okay, so here we go with our example. Traveling from Winnipeg to Fargo, your displacement is 420 kilometers south. Fargo, for those who don't know, is down in the States. So in order to go down to Fargo, you would have to go south. So we're going to start with our givens, and we've got our displacement, which is 420 kilometers, comma, S. Comma S is another way to write south because, you know, laziness, and I don't want to have to write out the whole word south every time. So we've got ourselves going 420 kilometers south. Well, what else is going on? It also says here that we're dealing with the trip taking 4 hours. Okay, so that's going to be a time. 4 hours. Now, of course, this trip doesn't tell us when the trip started, but here's the wonderful thing about when you start a trip. Most people, when they're saying, I'm about to start a race or I'm going to start a trip, they don't say, oh, I'm going to start my trip at 8:26 in the morning. What they do is they say, I'm going to start my trip now, whatever that is, and then I'm going to count from here forward. So it goes 0, 1, 2, 3, 4, 5, 6, 7. So the first number becomes a 0 just to make your life easier, because why do more work than you're going to need to? So there's our given. Now we need our equation. Well, our equation is very simple. V delta D delta T. You could write this in the expanded form, right, with the dF minus di, tf minus ti, but you don't really need to.
Arthur, can you please go to room 106 when you have a minute, please? That's room 106. Thanks.
Did you guys miss announcements? There you go. You've got some now. Oh, they were going to go again. Anyway, d over t, we have delta d already. And we have delta t, but why do we have delta d and delta t already when we haven't actually done any calculation? It's supposed to be final minus initial. Well, as I was just saying, when it comes to time, we start the clock timing things when we started the whole trip. So why do I care? I just made the initial one 0. In a similar vein for the displacement, my initial position is Winnipeg. I'm just going to set Winnipeg as my reference point. So Winnipeg is 0. Since Winnipeg is 0, it makes everything very simple. Right? Put another way, because, you know, some people, verbal math, it's always hard to listen to. If I write it out, delta D equals dF minus di. Well, if my final position is 420 kilometers away to the south, so we'll make it negative, and my initial position is Winnipeg at 0, well, any number minus 0 is just that number. This is the answer, because minus 0 doesn't do anything. So it just makes our life a lot easier. So there you go. Either way, we start filling in our equation. And we do our calculation. And we get V equals delta D is 420. Now, remember, 420 south. I talked in the previous video about how positive and negative means direction when it comes to physics. South is basically like down, right? It's down on a map. So if south is like down, that means that we can treat it like a negative. So we will. We'll just say it's negative 420. t is going to be 4 hours. Well, that's all we really need then. I guess we just plug that into our calculator and we work out an answer. And the answer we're going to get is 105 kilometers per hour. And it'll be negative because we were going south. Instead of writing it with a negative sign there, we could have done it a different way. Instead, we could write something more like this: 105 kilometers per hour south. Or, as already mentioned, I could be a little bit lazy because I don't want to write out the whole word south, and I just go 105 km per hour s. There you go. All done. Now you can even see it. Now, in terms of what this tells us, well, this is an average velocity, of course, because this is the total total displacement and the total time. And what do you notice? Well, 105 kilometers an hour. Speed limit's only 100. You guys were speeding. It's not a very cool thing to do. I get it though. You're in a hurry. It happens. Just, maybe next time, follow the law. Anyway, that's how to do this. What else can we look at? Well, flip over the page. We're going to get a very interesting problem. I like working through this one in class with everybody. So, as I mentioned already, this one here I'm going to suggest you guys sort of try with me. Obviously, I'm going to keep explaining it. I suggest you pause the video and try doing each of the steps because it'll help you with really understanding this, okay? So, take a little bit of time, take a little bit of effort. I hope you have some paper. At the very least, I hope you have your booklet. If you have it open on a screen, that's fine. I know I have, unfortunately, not had a chance to get you guys any paper copies, but, do what you can. Failing that, just take some notes on a normal piece of paper. It won't kill you to do that. So, here we go. We're going to erase this, and we're going to take a look at the next example. Now, the next example has a drawing that we're going to need. It's got a picture of a city block. Conveniently, in North America, and especially Winnipeg, a city block is basically a square. So, here we go. It says here, a city block is laid out in a grid running in the north, south, and east-west directions. What does that mean? It's a fancy way to say that it looks like this. These are the east-west directions. These are the north-south directions. Generally speaking, on most pieces of paper, a physicist will assume that north is up. Now, since I'm pretty sure you guys have learned your directions, but it's often the case where people kind of forget them. North is, of course, up, south is that way, east and west is the tricky one. West is to the left, east is to the right. Just a little reminder. This isn't the only way that you can set up these pieces of paper, but it's sort of the standard way. So, we've got that set up. What other information is there? Well, it says that it's running north, south, east, west direction, and it's 135 in the east-west direction and 45 in the north-south. So what that means is that on my diagram, I can put that this is 135 meters, and so is this one. And this is 45 meters, and so is this one. Okay, that's handy. It also gives us some markings. That'll be useful. So it says that this is A, and down here is B, here is C, and here is D. So let's take a look at what the question is going to ask us to do. On your bicycle, you travel from A to B during 9 seconds. Okay, I'm going to use a different color for this to make sure we can keep track. So our first question here, we'll do it right here. 1A. So you're going to go from A to B. Now remember, we talked about this 2-3 videos ago. That was the first video. How do you draw A to B? Well, you take point A and you take point B and you draw a line connecting them just like that. And there you go. A to B. So there's our A to B. And we've got ourselves 1A, and it's saying we go from A to B, and it takes us 9 seconds. So like normal, we're going to collect the information. The information it tells us is going to be 9 seconds for time. Do we note the distance? It doesn't tell us in the question. but it told us in the setup 45. Convenient. The question then actually asks, what is your speed? Okay, so speed is a v. So speed's what I'm looking for, and I have other pieces of information. Now our next step after writing down the given is we write down the equation. And at this point you have to remember what is the equation for speed. If you don't remember, you can of course look back. It is v equals d over t. Notice there are no arrows anywhere because this is a scalar. So it's no arrows, just like that. Now, once we have our formula and we have our givens, now we try to calculate. Okay, so we start plugging in some numbers. And here's where people can get confused, and this is why we write down the numbers the way we do. T is 9. I have seen students do this because they just assume the first number is the first number, but they're not, right? We have to make sure we put the right numbers in the right place. So it's going to be 45 over 9, and that will equal v. Finally, we're going to put our answer. V equals 5 meters per second. There we go. So we have solved the first question, or at least A. Now we're going to do B. Okay, well, I'll put B up above in this space here, and I'll do it in blue still, so that way it matches the picture. But let's think this through here, because B is asking me for velocity with an arrow. Velocity. Well, velocity is a vector, so it's going to involve delta D and delta T. Well, what is my displacement here? Where did I start? I started at A. Where did I end? I ended at B. I've got an arrow that literally points from one to the other. Incidentally, this arrow here is why we put an arrow on the top of the vector. This arrow is called a vector arrow because physicists are bad at naming things. Well, we know what this distance is. So the displacement is basically the same thing, right? It's still 45. It's not like the city block got longer or something while we weren't looking. But there is a bit of a small thing here because a displacement is a vector. And if something is a vector, that means that we need magnitude, aka a number, which we've got, it's 45, and we need direction. There are two things we need. Well, what direction is the arrow pointing? Yeah, it's south. So, S. There we go. Time. Well, it's the same amount of time, right? Same trip, same amount of time. So this just becomes 9 seconds. You can see here, this is why, as I mentioned previously, I put SEC for seconds instead of just S, even though S is more accurate. This is a case where Mr. C is doing something a little weird, just because he's trying to make things a little clearer. So we've got our givens, then we do our formula. Now the formula for velocity is change in position, change in time, and you'll notice these formulas look pretty similar. Really, the only difference is some triangles and some arrows. They mean very different things, though, right? So be careful. Don't get too lazy there. You're not fully trained physicists yet. You will be. Just give it some time. We start putting in the numbers. 45 over 9. Now, we've talked before. S, south. That's basically negative. So I'll put a negative sign in there. And of course, that's going to be equal to V. Then I put a final answer, and it's going to be V is equal to negative 5 meters per second. The two numbers are the same. There is a difference, admittedly, right? This one over here is just 5 meters per second. This one up here is negative 5 meters per second. That's a critical difference. We have to keep track of that. Because, of course, This one is a scalar, so it doesn't really care about direction. It doesn't care which way you were going. But this one is a vector. This one does care. That's why it needs a negative. Reminder, another way we could write -5 is we could just simply say 5 meters per second, comma, south. Means the same thing. So there we have it. We've solved the first question, and I just spent all this time telling you that velocity and speed are different, and yet here we look at these, and they are exactly the same, except one's got a negative sign and the other one doesn't. Doesn't seem all that different now, does it? Well, let's try question 2 and see. That's Mr. C for you, constantly finding ways to make things more difficult. So I'm going to erase the blue. For question 2, we've got a different path that we're walking. Well, riding our bicycle, I should say. I wonder how many people actually have bicycles these days. Okay, we're starting from the same place at A, and then we're doing a different walk. So instead of going just A to B, it says that we go from A to B, B to C, and then C to D. Now, usually if left to their own devices, quite a few students will finish the square and go from D to A, even though it doesn't say that in the question. It's just because, humans are very good at finding patterns, and students are especially good because, patterns, if you can find them, make work easier, and then you can be lazy. Unfortunately, this doesn't take us all the way back, at least not yet. That'll be question 3. Anyway, let's set this up. It says, the first thing it's asking for us is, what is the distance traveled? The distance. So I'm looking for, this is going to be 2, and I think in your notes it says C. It should really say A, but whatever. Distance traveled. What's our distance formula? Oh, it's been a while. Do you remember? If not, you can look it up. Yeah. Could be. Could be something kind of like that, right? So in order to solve this distance formula, I'm going to need some distances. Well, I've got a bunch, right? 1, 2, 3. I got 3 different lines. Those 3 lines correspond to 3 different distances, which I can throw into the formula. So D1 is going to be 45 meters, D2 is 135 meters, and D3 is 45 meters. Very nice. So I start filling in those numbers. For space, because I do have a limited amount, I'm going to put in the equation underneath as opposed to next to it. So here we're going to get a 45, a 135, and a 45. So the total distance is going to be 225 meters. That's how far you go. It's pretty far, to be honest. But what's the next question asking? The next question asks, what is your displacement? That's a little trickier to do, isn't it? In order to do it, obviously everyone immediately starts looking to this math we already did, but we're not asking for something different. Looking to this math doesn't help us. So what is displacement? What's the definition of displacement? Well, it's the separation from the start to the end. How far I am from where I started. Where did I start? Started at A. Okay. Where did I end? I ended at D. The separation from start to end. And it's a straight line. It's always a straight line. Well, if we look, that's a straight line. And it goes right from the start to the end. That's a weird one, isn't it? Like, realistically, you went all the way around the block. But for the purposes of the math, it doesn't really care. Remember when I drew the little picture of your house, your incredibly skinny house, and then I made that very nice house for your friend? Remember how I showed you that the displacement was just a straight line from where you started to where you ended, just like this? Well, guess what? It's the same thing here. Sure, I started up there at the top, and then I went down, and I went over, and then I went up. But as far as displacement is concerned, that doesn't matter. Displacement is just from start to end. You just happen to take the long way because apparently you can't get down the road there. I guess there was construction or something. I don't know. So when it comes to doing the calculation, my initial position was 0. And my final position was 135. Positive or negative, though? Well, we generally said earlier on that if it's left, it's negative. West is also generally negative. So this one here will be a negative meter. We draw out our equation. df, di. df is negative 135 minus 0. Delta D equals negative 135. Meters. See what I mean when I said that often these equations become very simple because we usually make our starting point 0 because it just makes our life a lot easier. Why do more work than we strictly need to when it doesn't really give us anything? 135 explains it pretty well. It's negative, which of course is another way to say 135 west, which we could also write instead. We could write 135 meters, comma, W for west. So there we go. That's how to do 2. Not bad. But this is the velocity page of the notes, and that's distance and displacement. So what in the world is Mr. C doing? What he's doing is building up slowly towards the final answer. So let's take a look. Flip over the page. And we see here that question 3 says, the journey number 2 took 55 seconds. Calculate speed, calculate velocity. Okay, fair. I'll use it in green here. And what we're going to have is that it took 55 seconds. Okay, well, the distance was 225 meters. The time was 55 seconds. We set up our equation. V equals d over t. D is 225 over t of 55, and that's going to give us 4.1. Okay. There it is, 4.1. What about velocity? That one's going to be complicated, right? There's a much more complicated formula. We're going to have to do more steps, right? More things. Except kind of no. I'm going to do velocity in orange here. We already know the displacement. We said that it was negative 135 meters. And the time is still 55 seconds. My equation is delta D, delta T. I just plug them in. I already did all the math earlier when I did them up here. So I don't have to do anything fancy. I just put the numbers in. 135 negative over 55, and that's going to equal 2.45. And that is squeezed in as tight as possible there. Here, let me move to the other side. So what are we seeing here? Like, what's going on? The first question we did, the displacement, the speed and the velocity were exactly the same. One of them had a negative sign, one of them didn't, but otherwise the numbers were the same. Here they're totally different. This is where everything gets messy for kids. Well, adults too, to be honest. What's happening here is that we got to understand that these two things are measuring something different. As I said with my terrible sports analogy earlier, just because the defenseman and the goalie are both playing hockey doesn't mean that they both follow the same set of rules. Displacement is a straight line from start to end. Distance is the whole trip. You can almost imagine it like this. If you started at A and you went B to C to D, and if you traveled at 4.1 meters per second, you would arrive in 55 seconds. Okay, so I'm telling you what would happen. If you went that fast, you would get there in slightly less than a minute. Okay, great. So what? Well, if your friend decided to leave from A and go straight to D as a straight line, if he went at 4.1, he'd get there first, obviously. He doesn't have to travel as far as you do. You're taking the long road, the scenic route. They're taking the shortcut. So in order for them to arrive in the same amount of time, and you'll notice both of these use the same amount of time, the other one, the displacement, has to be slower. The velocity has to be slower. And that's what we see. This velocity is, like around half as big because you cover a tiny, tiny distance. Why are these two things showing different things? Because they're measuring different things. One of them, the displacement, the orange and this red up here, is talking about going from A to D directly, a straight line. This one and the green one are talking about taking the long way. That's the difference. They're talking about different things. The fact that they have two very similar sounding names just makes it confusing. If all of that made sense to you, you're in a good place. If it doesn't, that's okay. Send me some questions. Ask. Now, we've got one more question. Because, of course we do. I do want to give you guys a challenge. So, let's erase this. And we're going to do our last question. I already mentioned what it was, and of course you have your booklet so you can see. What does it say? Around the block. What does around the block mean? It's a fancy way, and by fancy I mean a standard English saying that means that you have gone the entire perimeter of the square, or rectangle in this case. So what that means is that you're starting at A still, because we want to keep it simple, and you go down to B, and then you go from B over to C, and then you go from C up to D, and then you go from D to A. So now we have gone around the block. It also tells us that it's going to take 90 seconds. Okay. T equals 90 seconds. We'll just write that down because we're going to need it, obviously. The question then asks you to calculate your speed and your velocity. So it's everything we just did in the previous question, 2 and 3, broken into, instead of being broken up, it's now combined into one step. You can still do it. You still know how. I'm going to do each one of them in a different color. So I'm going to do my speed in red. So let's do speed first because speed's pretty easy. So I'm looking for speed. So I'm going to put V question mark with a little circle around it. And, well, I don't have anything yet. At least, not yet. But let's put things together. I know that D1, D2, D3, and D4. I have all of those because they're all up there. I've got 45, 135, 45, 135. So let's do this in a couple stages. There are a few ways you can do this. The easiest way, of course, is to do it one step at a time. And I do strongly recommend that, especially when you're first learning. So that's what we're going to do. So we go, the total distance is equal to D1 plus D2 plus D3 plus D4 in this case, because there are 4 distances. Then I put in my numbers. 45, 135, 45, 135. Remember, that's a sigma. That's what that squiggle is in the front there. That means add everything together. Well, when I add everything together, I'm going to get how much? Well, it was 225 and for the last question, and I'm adding an extra 135, so I guess that would make it 360 meters. Sweet. So usually at this point, most students will be like, yes, I'm done. I did math. Yeah, well, unfortunately, that's not what the question asked for. It's one of the reasons why I like to scribble down what the question's actually asking. It is asking for the speed, not the distance. Make sure you know what you need. All right, so we'll do it over here. The speed is equal to d over t. Well, d, we just said, was 360, over t, which is 90. We get v. We put all that together, and we're going to get ourselves a nice, solid velocity of 4 meters per second. By velocity, I obviously mean speed. So there it is. We've done it in multiple steps. Great. Now let's do the hard one. We'll do that one in blue. Okay, vectors are always super challenging, right? They're always very complicated, so let's do it step by step. How do we set this up? First, we collect all the information that we have. Okay, well, time is 90, of course. We're going to need the displacement, and we got the time, and we're going to need to find the velocity. So velocity is our question mark. Okay. Well, as we saw down here, first we got to get the displacement, then we can find the velocity. Okay, so let's find the displacement. Where did I start? Okay, our initial position was, well, it was 0, right? We started at A. Okay, great. What's our final position? It's also 0. Wait, what? What do you mean it's also 0? Well, we went all the way around the block. We started here, then we went down, then we went over, then we went up, then we went over again. We're back where we started. What does that mean? Well, the equation is final minus initial. What's 0 minus 0? It's 0. Huh. Does that make sense? I mean, displacement is the separation from start to end. My start was here, my end is also here, so there's no separation, there's 0 difference, so it's just 0. We're done. Okay, but we're not looking for displacement, we're looking for velocity, so we have to calculate the velocity now. That's going to obviously be very complicated. Well, actually, no, it won't. Because the equation for velocity is just delta d divided by delta t. Delta d is 0. So 0 divided by 90 is 0. So the velocity is 0. Huh? That always confuses everybody because they're like, I don't understand. I just went for this jog around the whole block. I traveled a total of 360 meters. What do you mean my velocity is 0? Well, it's very simple. You started in one place and you ended in that place. The velocity tells you the speed, the pace you would have to set to do that journey in a straight line. And a straight line from where you are to where you are is nothing. If I'm already here, I don't have to go anywhere to get back. If I left, then I'd have to figure out, okay, how much is this distance and how fast do I have to go? But no, I'm already here. I'm done. I don't have anywhere to go. And this is what I mean when I say that displacement and distance are measuring very different things. Displacement only cares about the straight line distance, straight line separation between 2 points. If there is no separation, then displacement is 0. And if the displacement is 0, the velocity is 0. Weird, I know. But that's why displacement and distance, speed and velocity, that's why these exist. Each one of them is used to describe a different thing. Now, at this point, you're probably thinking, I don't understand the purpose of this. I mean, the zero number that you just got right there doesn't seem very useful. Like, what am I going to do with it? In this case, it's not very useful, but it's useful in other situations. Physics ends up dealing with some pretty weird situations, you know. Okay, if you guys take a look at the next page here on page 21, you guys have some more examples that you can try. You've also got more examples on page 22. Page 21 has the setup like so it shows you all of the little boxes. Page 22 onward does not. It just simply shows you guys questions with some space for you to write it out. Please keep yourself organized. In terms of the answers, so I will put up answers to 21, but for anything on page 22 onward, the answers are actually located at the bottom of page 24, so you can look up and see if you're doing it right. You can also notice the next thing that we're going to talk about, which I will probably make a video of next week because we've got a lot to do already, and that will be acceleration. Now, before we get into acceleration directly, I will probably try to put together a quiz on velocity. You are, of course, welcome to do it at the pace that you set. So when you are ready, you are welcome to go for it, okay? So don't worry if you're feeling as though you are falling behind or anything. You have time. Take it easy. Ask questions. We'll get through this, all right? Okay, ladies and gentlemen, thank you, and I hope you have a good rest of your day.